Thank you, Dr. Munmuz Jha and Dr. Vimal Kumar for inviting me, and the Liberty Institute, of course. It's a pleasure to be here. And I'm glad that this meeting is actually being organized by HS Department and the Economics Group, for sure, because eventually the climate change, if anything would matter, it's ultimately the economics of the nation or the global economy, whatever it is. So after all, money matters, right? So glad that this activity is being done by the Economics Group. And my job is fairly simple and complex at the same time, because I've been given the job of introducing the subject and setting up the stage for discussion. More technical papers, more technical presentations will actually follow. But I will start off with very simple things. I know that this is a very diverse audience, and I'll try to put things in the correct perspective so that the further presentations will actually follow from here. Now, putting things in context, the Earth was formed 4.7 billion years ago, long time ago, of course. Most of us know that. Humans emerged about 250,000 years ago. And we are the 800th generation of the Homo sapiens. Most of us know that as well. But out of this, the first 600 generations lived in caves. But then, we are now also 6th to 8th generation since the mechanical power replaced the animal power. We are 4 to 5 generations since the cars were invented, and of course boomed eventually. Can somebody switch off this light for me? Might be better for the. And then we are also, by the way, the first generation with with the intensity of the economic development that our presence is starting to feel or to be felt by the planet's total ecosystem. In a way, you can see the curve of the population as it has gone up from 1800s to something like we are now this is the kind of a growth, exponential growth of population we have seen. We are also the first generation to understand, by the way, the collective impact of this growth and that of the climate change, which will come later. And finally, we are also the first generation with the opportunity to redefine our relationship with the planet. And that's where the challenge actually lies. It is not just understanding how the climate system as a whole works, but it is also about how do we work, how do we live with this changing scenario in the climate system as a whole, essentially. We have moved a long way from hunter-gatherer stage to the agrarian stage to a very large boom in the industrial revolution, for example. But then we have also paid a price for that. And that is what we are looking at today in terms of the climate change scenarios. I'm sure you can't read this, but this whole idea of putting this up was that this was an article by the Ban Ki-moon, who was the then Secretary of the United Nations. And this was also the year when the IPCC 2007 was released. The first report was released. And the part which is yellowed here that basically says he emphasized in the first UN conference on climate change, and he urged the nations to work with some urgency to combat or to mitigate or to adapt to the climate change scenarios. This was one of the first few articles when there was a public public admission that there is something called a climate change in a way, and something has to be done about it with a lot of urgency, essentially. Since then, we have moved a long way. We know, you can see a list of things here. If you look at the points, the issues which we now know with a very fairly well about that is, of course, that there has been increase of the greenhouse gases. That's firmly established. Increase in the global average temperature, very well established. Weather indicators of climate change, we know quite a bit about that, 66 to 99%. And then, of course, we also know and understand the causes of the global warming as well. Now, but then what is a little less known in a way is the consequences. Some are well known, but many are uncertain, because the scenarios, the future predictions, as we will we'll see later, is much less certain than we think. The solution to the problem is well understood but not acted upon. That's the problem. And the prospects of initiating a solution by the industrialized nation is extremely uncertain. And that is the saddest part of the whole story here. Now, before we get along with this, let us first try to understand what is this all about, the climate change scenario. I'll spend just 2 or 3 slides on this. climate system is a very complex system. It's an interaction between 5 different components of the Earth system: atmosphere, vegetation, ice, land, and ocean. All of these are basically interacting amongst each other, and on your left, you see this is something which climatologists often call as the forcing functions. And these forcing functions range from the effects of plate tectonic, which operate at a millennial scale, to the changes in the Earth's orbit parameters, which operate at a several thousands years scale, and then, of course, to the smaller scale changes of the sun's strength. And on the top of that, we now superimpose the anthropogenic impact, which are obviously lasting for the last few hundreds of years. And what you see, when these forcing functions, ultimately act upon any of these 4 or 5 system, parts of the Earth system, and of course the internal feedbacks, what you see is a change in the response, which is basically what we call as the internal response system. You see a change in the atmosphere, in the ice cover, in the vegetation, in the ocean, and of course on the land surface. And that is what we normally see as a manifestation of this climate change. One of the things, let's not worry about the plate tectonics, millennial time scale, and so on. We'll move on, to smaller scale systems. But then one real discovery which I must mention, and that is where the entire genesis of the climate science actually started off, and that was a very famous Russian, astronomer called Milankovitch. And he, based on the astronomical concepts, he basically predicted that 3 basic parameters of the Earth's orbit, the eccentricity, tilt, and precision, they ultimately control the total amounts of insolation which is reaching the Earth's surface, and they have a very definite cyclicity, for example. So eccentricity has a cycle of something like 100,000 years, tilt has a cycle of about 40,000 years, and precision has a cycle of, for example, 23,000 years. And these cycles are now known. For example, the precision cycle is now known as the famous glacial interglacial cycles, because we know that the Earth has changed from a glacial ice ages, for example, to a non-ice ages, or what we call as a glacial and interglacial periods, and so on. But then, his science went almost unnoticed until this paper, famous paper by Hayes et al., appeared in Science in 1976, and that paper was titled as "Variations in the Earth's Orbit, Pacemakers of the Ice Ages." And that was probably one of the most famous papers to start with, which ultimately established the whole concept of climate science. And what he said, that for almost, he basically presented Milankovitch data for almost 500,000 years and showed how the climatic changes in the Earth's system has actually followed the variability in terms of the Earth's obliquity and the precision. That was the beginning of the climate science in a way, in many way actually. Then, just to impress upon you the time scales, the climate change is something not new. It has been, the Earth has seen several phases of climate change over its history, and as you can see, the time scales at which the Earth has experienced these changes are extremely variable, from 10 to the power 9 years, 10 to the power 8 to 9 years, at which the tectonic processes, the Earth's plate tectonic concepts, basically, they operate, all the way down to 10 to the power 2 when you start looking at anthropogenic forcings at a global scale, and then about 10 years of time scale for anthropogenic forcing, regional scale, local scale, and then, of course, a few seconds or a few minutes of the meteoric impact or the volcanic forcings have also affected, for example, the climate, Earth's climate in a very major way. For example, one of the major, volcanic eruptions, the Pinatubo eruptions in Italy, that changed, or that basically lowered the global climate by almost 0.5 degrees centigrade for almost 2 to 3 years. So there are scales which we have to be worried about, and that's what I will come back to in a minute. That it is a scale we should be worried about. It is not really the change what we are really concerned about. Now, let's look at the change, the trends. How did it all started, essentially? People started looking at the data. People started looking at historical trends of the temperatures and rainfall and so on. So this is again one of the very early data sets which I am showing you. This is the variation of the Earth's surface temperature for almost, the first graph on the top shows the variability in terms of for about 140 years. And you can see, around about 1940s or so, which is also the period of industrial revolution, that's the period when you start looking at the temperature curves rising quite suddenly. But if you look at longer time scales, for example, the last 1,000 years of time scale, for example, for the northern hemisphere, again, what is striking here is this rise here, which you notice. Suddenly there is a jump here, for example, and that is what people have been actually worried about. So let me show you the next slide. I will show you a zoom up of this slide, and then you can understand that better. So here is a graph which shows the global mean temperature. So there is a general rate of rise, which you can see, right from 1860 to something like 2000 or so. It's a little bit old data. But what is important to note here is the rate, how these rates have changed through time. So look at this rate here, which is, for example, for about 150 years of rate. That gives you a value of 0.045 degrees centigrade per year. That's the rate when you look at the last 100 years. That's the rate when you look at the last 50 years. And that's the rate when you look at the last 25 years. And that is the main issue which we are worried about. It is not the general increase of the temperature. It is the time taken to reach that level. It is the rate at which the temperatures are increasing. That is what are basically worrying the scientists, policymakers, and the engineers all along. So the question, and then of course there are independent records which basically show you that these are the 12 warmest years which we have, and these are again the global data set. There are local variabilities as well, but these are the 12 warmest years which have been recorded globally all across the world, for example. Falls somewhere here. I mean, since this is the data since the formal measurements of the temperature actually started off. Now, if you also look at the longer data sets, for example, this is again, I'm switching the time scales, quite frequently, but this is again a time scales of something like 600, thousands of years. And again, if you see, again, to emphasize the point that the temperatures of the Earth, this is again, you can take them as a proxy for temperature because this is a carbon dioxide concentration. And we know now that the carbon dioxide concentration in the atmosphere is directly controlling the global temperature. So that shows you the trends again. And this is, so there is some kind of cyclicity which you can see here. This is basically the methane gas variability, and then so on. So the point is that, but then the point is that at any given time, in the last 600,000 years or thousands of years, the amount of increase which we now see, or the amount of levels of CO2 and CH4 which we now see, for example, in 2005, has never been as high as that. And that is the cause of the worry, essentially. Okay, now let's look at the other issues, for example. Okay, one can also argue that why isn't all of this change is attributed to the natural factors. Let's look at the separation between the natural increase or natural part of the increase and the anthropogenic factors. This is the total observation. This is the actual observation data from 1890 to 1919. This is basically the natural part of the variability. Okay, and as a part of this, we should have actually seen a decrease of the temperature because we are supposed to be moving from an interglacial period to a glacial period right now, right? But that doesn't happen, So therefore, a part of this increase which you see has to be anthropogenic. There is no, because the modelers have done this job already, and they have separated out what should be the amount of natural increase or decrease of temperature through time, through this time scale essentially, and that seems to be the trend should have been something like that, but what we see is something like that, and that's obviously the anthropogenic part of the increase of temperature which we actually see at. Now let's move to India. This is the Indian scenario. This is the annual mean temperature variability over India, between 1875 to 2004. Again, the trends in the temperature is quite similar to the global trend, but you can again see a much faster rate in the last 50 years or so. That is a trend which is basically data coming from the Indian Meteorological Department and so on. Now let us also try to look at the historical data set which we have for the rainfall for example. These are again, the rainfall data set plotted from 1800s to something like 2000 data sets. And again, you see that these are extremely variable. There is no real trend which you can see here. And so there is no trend, there is no increasing trend in the monsoon rainfall as far as this data is concerned. There is of course a lot of inter-annual variability, but there is no significant trend in terms of the increase of this data sets as such. But then, the next part of the job what people have been doing is to trying to predict. This is again a work from Dr. B. N. Goswami now at Pune, and these are the future scenarios for projections in terms of the rainfall, and the lower one is for temperature. Now, what do you see here? All you see is a chaos, absolute chaos. These are obviously different kinds of models which have been put together, but you can still see some sort of a trend here, increasing trend here, and so on. But the basic problem in all of these models have been that this is not too bad actually. This is not too bad in terms of the prediction. So temperature is easily has been modeled quite effectively, and so the future predictions for the temperatures have a much smaller range of variability. But what has been a problem for us as of now is to be able to model the actual amount of precipitation, the futuristic projections for the rainfall, and that ultimately translates into water. So what will be the availability of water through precipitation? Of course, in future, that has been a major issue, and that ultimately I'll come back to this in a minute. That ultimately relates to one of the major impacts of the climate change, and that is going to be on the water resources, which the next speaker will also cover in a minute. Okay, so so this is where we stand, at the moment in terms of the status of the data. How did we pick up? How did we learn about the climate change? Where do we stand in terms of the modeling? There are detailed reports available on the net, IPCC reports. Now the next set of reports is now coming. They're already available in parts, at the web and so on. So these are still under revisions, and some comments have been invited from people and so on. But in a nutshell, if I have to summarize, where do we stand in terms of the climate modeling, is that the projections of, particularly in terms of the Indian monsoon systems, it's really complex. The Indian monsoon system is really complex to model them, and most of these models have still not reached a level which can be called as reliable, for example. And the reason is that these are really complicated systems to actually model. But then, a moment ago I said that the ultimate objective of these models is to be able to predict what will be the rainfall variability, or what will be the hydrological system, how will the hydrological system will respond, and so on. And these are, for example, some of the important questions which we are still looking for the answers, for example. So hydrological cycle as a whole, and the monsoon system in particular, we are still struggling to find how they will behave in the next 50 to 100 years of time scale, for example. What will be the quantum of the rainfall increase, and if so, how much, and so on. What would happen to the extreme event? Even if, for example, you assume that the total amount of precipitation over the year or in a year is going to be constant, how will that how will the variability of that system will actually change, and that will ultimately translate to the droughts and the floods, for example. How will the pattern of the precipitation will change, and how will that translate into the hydrological behavior of the whole system, and so on. These are the questions which we are trying to answer, for example. And eventually, what will be the relative contribution of the greenhouse gases compared to that of the aerosol, which is, another speaker, Sagnik Dey, is here. He might talk a little bit more on that as well. So, let me spend a few minutes now on the climate change impacts and the challenges, and many of these things will come up again and again. Now, this is a quick summary of what are the likely impacts of the climate change which we are looking at. Starting from health, of course, the weather pattern, if that is going to be, So, starting from the health issues, the weather-related mortality issues, the disease and air quality and so on, to agriculture, which is going to see a very major impact, not just in terms of the total amount of water availability, but also in terms of the pattern of the water availability. So the crop yield as well as the irrigation demands are going to change. The forest covers, the areas where the precipitation is supposed to be increasing, they will of course show an increase of the forest cover, but then many areas will actually show a decrease. So the composition of the forest cover will change, the geographical range will change, the forest health and reproductivity will change. Then the water supply, of course, as I mentioned again and again, water supply in terms of both quality and quantity, that is going to be affected. The competition for water is going to increase, and people say that if there is going to be a third war at all, this will be about the water actually, and not on the oil for sure. The coastal areas are going to be affected very severely because of the sea level rise. A lot of glacial melt is going to increase the sea level in a very major way. The erosion of the beaches, you will see this inundation or the reappearance of some areas will actually happen. The species and the natural areas will also change quite a bit and so on. So let me focus on a few things. Obviously, I'm not an expert on all of that. So I will focus on a few things where there is some clarity is now emerging and some more information on the impacts that are actually emerging now. So to start with, I will spend a little time on this, the impact of the climate change on water resources and hydrological cycle. The next speaker will cover that in much more detail. But the key issues which we are trying to understand or which we want to know answers are basically how will the precipitation be affected by the increase in the atmospheric water vapor content. How will the precipitation pattern will change, for example, and how will the risk of floods and droughts, the extreme events as we call it, they will change. How will the change in the soils and soil moisture runoff will be affected, and that again has implications for agriculture and water supply. The ice melting, reduction in snow cover, the sea level rise, for example, and so on. Now, what we know as of now, whatever we know, in terms of the climate models and the hydrological response of that, but then there's still a large amount of uncertainty, is there because first of all, because we do not know, for example, if you talk of the water resource utilization, we have very little idea as to how much water demand is going to be in the society in the next 20 or 30 or 50 years, for example. We have very little, data on the projected socioeconomic development, and that's where the economics and socioeconomics also comes into picture. The emission scenarios in the climate models are not taken care of, in a very effective manner. The downscaling is a major issue because we are still using the large scale models. They have to be downscaled to regional scale and then to a basin scale, where we have very limited observations and then of course very incomplete understanding of the whole process, the complexity of the process essentially, and so on. So there are a lot of research challenges and needs which we can think of, in terms of the water resource development and the impact in terms of the climate change, for example. Now, focus on rivers. I mean, that's basically a domain which interests me in a very major way. The India's water resources have to take into account all of these issues. For example, the increasing water demands, the water assist scenarios, and the future of water resource development plus the demands. All of that plus the possible climate change mitigation scenarios, and all of this will be ultimately affected by all of these climate change related scenarios. For example, the melting of the glaciers, we do not know what will be the impact of that melting, in the due course of time, sea level rise, the increased incidence of floods, and so on. Then the water resource development itself will have to be developed in taking care of most of these are basically your anthropogenic factors which we are still uncertain of. The variations in the water availability in time and space, the uneven distribution of water resources. We know that the availability of water in Rajasthan and Gujarat and compared to Bihar and UP are quite different, and so there is already a water stress in many parts of the country. We are very highly dependent on the monsoon systems, and then of course we have a lack of the environmental considerations as well. Okay, I will quickly go through this, a few slides here. The other issue which we have to be worried about is how will the individual rivers, work, essentially or behave in a changed hydrological regime. And most of the models are suggesting that because you will change the overall pattern of the hydrological response, they will also start behaving in a very, very different way, for example. Okay, I have to hurry up a little bit, but then again a major impact is going to be on the agricultural output, productivity, for example, and all of these issues which are the primary effect as well as the secondary effect which are related to the agricultural productivity, that is going to be affected, for example. Crop yield and farm incomes in India. There is already some data which is suggesting that how the yield gets affected in terms of the air temperature variability or the precipitation regime, for example. Then Okay, so let me focus last 2 minutes on what are the major challenges which we are looking at. We are looking at a scale which is very, very different. The climate system operates at very different scales. We are looking at a knowledge base. There is a mad rush to blame everything to climate change, which is not actually true. There are so many of the anthropogenic impacts are not simply because of climate change, but also because of an overexploitation of the resources, for example. There are policy issues. There is a debate going on between mitigation and adaptation, for example. Adaptation strategies for whom, for what, and for how? How do you do that? There are trade-offs involved. There are adaptive learning mechanisms involved. There are system interventions involved. All of that has to be taken into account, including, of course, the community participation. So what do we need is we need triple I's. We need information, we need initiatives, and we need implementations, for example. And that has to be done with a clear emphasis on the equity, economy, and environment. That is basically the message I wanted to give. 2 slides on what are we doing at IIT Kanpur. We have an informal group of climate change research at IIT Kanpur. We have almost 13 to 14 people involved. These are the different kinds of focuses which we have. We look at various scales of climate change, the long-term scales, the impact on water resource and water hydrological cycle, the paleoclimate, the past climates, the last 10 to 20,000 years of time scale. There is a group which does modeling, for example. You will see some of those results now. And then, of course, there is a strong participation from the economics department as well. We are trying to integrate the economics and policies of climate change as well in terms of that. These are some of the specific projects which we are looking at. At the moment, we are focusing on the Ganga Basin, for obvious reasons that it is the largest, basin, one of the largest basins in the country, not just in terms of the size and the water availability, but also a food basket of the country, for example. So, the way forward, my way will be that first of all, we need to understand how do we tackle this? This big debate of mitigation versus adaptation. We need to also understand that the solutions to the climate change in different parts of the country, like India, for example, has to be very different because we have differential sensitivity to the response to the climate change. You cannot have the same prescription for different parts of the country. And then, of course, there are specific issues about how do we manage the water resources, how do we improve the quantitative models, for example, how do we improve the water land management, for example, and so on. So the message is that the climate change, of course, is a global phenomenon, but the solutions have to be much more local than we actually think about. So I will stop here, and if there are questions, I'll be happy to answer.